All right, so now for section 1.4, we are going to be doing limits and doing a few more pieces of terminology that we will use in terms of these limits, but more focusing on the continuity right now. And then at the end, we'll look at the properties. So it's actually very easy to figure out what the limit is based on the graph of the function. However, that can be pretty time consuming. So what we actually want to do is try to figure these limits out algebraically. And so after we go through some of these continuity terms, we will be looking at the limit properties, which I have in this handout below, which will also be posted on the Angel site. And you don't have to copy this, you're just going to print it. It's also on page 35 of your textbook. All right, so if we continue, we have a jump discontinuity. And what a jump discontinuity is, that's at the value x equals a, and so you've seen this before, as x approaches a from the left and x approaches a from the right. Those are those little pluses and minuses there, so I'll just get rid of those. And if the one from the left equals L, where L being any number, and the one from the right is M, M being any number, as long as L does not equal M, this is a jump discontinuity, which basically means that if you have a graph, and let's say your function is coming like this, and then you have to jump down here and go like this, like we said before, if you have to lift your pen from the paper and move to another spot, that means it's not continuous. And so here's an example where we would have to jump from this function down to this function, and this value, let's say a, might be 2, and this value at this same a value might be 1. So these do not equal, therefore a jump discontinuity. An infinite discontinuity, that occurs when there's a vertical asymptote. So for example, we have this, and we've seen these before in advanced functions, and we'll say there's another horizontal there. And if this is the case, this is showing that our y values here are increasing or decreasing, whichever direction you're going, but they are going to infinity, which means they have without bound, or they are not bound. They are not going to one value. They will keep going and going. Okay, well, this is where the good stuff happens, and this is the removable discontinuity. And this function for f is still at x equals a, and so you'll see this is very consistent here, where a is a number. And if this limit equals L, and either the f of a equals L, or f of a does not exist at all, this is a removable discontinuity. So what that might look like is if you substitute in this value, which should be the first thing you do every time. This right here, direct substitution, you should substitute that value in every time. Once you substitute that value into this, and if you end up with something of 0 over 0, infinity over infinity, you will see here with these cases that it does not exist. You cannot divide by 0, you cannot have infinity over infinity, and this is called indeterminate form. And so this is where the removable discontinuity comes from, is if you end up with an indeterminate form. Now how do we fix this? How do we remove that indeterminate form? We can do that by factoring, rationalizing, expanding, and simplifying, which are all of the ones we've talked about. Doing the conjugate, okay, those are all strategies to help get rid of a removable discontinuity. Now when we look at the limit properties, which is this handout right here, which is also on the Angel site, so make sure you print it, you can see that there's a list of properties here, 7 properties that you can do to solve these limits. So for example, we have here, if the limit k of as x goes to a is k, that will equal k, it's a constant. If the limit of x as x goes to a, this will equal a, because the first thing you should be doing is a direct substitution of that a there. And so you can go through each of them. If you have a question, let me know, but make sure you print this, and then there's a few examples at the bottom for you to try. That's all. Monkman out.